4, 3, 2. Greetings and welcome, friends. Today we're continuing our kind of analysis. I almost said analyzation of graphs. Yesterday we talked about continuity, and today we are going to continue with, although it was discontinuous, I suppose, because there was a break in between the two lessons. But sadly, whatever. We'll keep going. End behavior. We've seen this before back in the days of math freedom. And end behavior describes what the y values do as our x values. Here it says the absolute value of x becomes greater and greater indefinitely. So here's an example. It says determine the continuity at x equals 2 and the end behavior. So I'm kind of two birds, one stoning this, if you want to think about it that way. So here's my function. I've got f of x is equal to x minus 2 all over x squared minus 4. And let us analyze this tabularly. I'm just making up words today. X minus 2 over x squared minus 4. Now, here's a little Google Doc sheet that I'm going to give you. And the way you deal with this is, you guys can't see that online very well. You enter your formula in the y column like so. So let's see, what was that equation? It was like x minus 2 or something. Oh, I've got it right here. I'm good. So equals, and instead of x, I'm going to click on this cell right over here. X minus 2, close parentheses, divided by, open parentheses, this guy, squared, I'll use the caret to the second, minus 4, close parentheses. And so what I'm doing is I'm essentially plugging in this value for x, and it's going to give me the y value as if I plugged it into the function. I hit enter. That gives me that particular y value. But I want it to give me the y value for all of these x's, all those fools there. So I'm going to move my cursor down to the lower right corner until it becomes a plus sign, and then click and drag. It duplicates that formula all the way down, and like so. Now, I'm actually interested in a particular point at x equals 2. So the c value is kind of the center. So I hit x equals 2. Let me grab a nice little snapshot of this, and we shall do our analysis based off of this. So, analyzing this, let's consider the continuity test. Part 1 of the continuity test, does the function exist at x equals 2? No, it doesn't exist, because notice it gives me this hashtag div/0 factorial. That's not at all what it means, actually. It's just divide by 0 error is what it's giving me. Because notice if I plug in 2 here, 2 squared is 4, 4 minus 4 is 0, dividing by 0 does not exist. So it fails part 1 of the continuity test. Part 2 of the continuity test is, does it approach the same value from both left and right? So notice, what is it approaching from this direction? It appears to be getting closer to 0.25, right? And here it appears to be getting closer to 0.25. So this one seems to approach the same number from both sides, if I'm not mistaken, friends. And then part 3 of the continuity test is the number that it approaches from both sides the same as the number that it is at that point? Well, it is not at that point. It does not exist, DNE. So therefore, part 3 fails by default because either part 1 or 2 or both failed. And therefore, part 3 fails. So it is discontinuous at this point. So discontinuous. Now let's talk about end behavior. I'm talking about really, really big values of x. So, or really, really largely negative values of x. And when analyzing this, the best thing to do, notice that my little table here automatically is plugging in like -10, -hundo, -thou, and then +10, +hundo, +thou, thou. And so it's kind of simulating those big negative numbers, those big positive numbers. So as x gets more and more negative, what does this appear to be approaching? Yeah, it appears to be approaching 0, if I'm not mistaken. And it appears to be approaching 0 specifically from the negative side, if I might say so myself. And here, it's approaching, looks like those numbers are getting smaller and smaller. It's approaching 0 and from the positive side. So if I wanted to describe the end behavior of this graph, this is how one would do it. This is the end behavior. All right, it's analyzing what's going on with y as x gets really large or negative. So this is how I might say it. I could use y, or I'm going to use f of x because they mean the same thing. So the output, or the y value, approaches 0. In this case, it is approaching it from the negative, but it's approaching 0 as x approaches negative infinity. Right? And then what's happening here? The y value, f of x, is approaching 0 as x approaches positive infinity. So end behavior is just an analysis of what's going on in those really extreme cases. We've seen it before when we kind of analyzed horizontal asymptotes, which in fact this one does have a horizontal asymptote. Y equals 0 would be that equation. And what's interesting about this particular graph is it actually is a graph with a hole in it. Because if I was to factor this part here, that's x plus 2, x minus 2. And then I could have canceled out the x minus 2's, but in doing so, I'm actually partially eliminating a legitimate answer, or actually, no, I did the opposite of that. I'm allowing an illegitimate answer into my problem if I don't consider the fact that the domain was restricted, where x could not have equaled positive 2, because positive 2 would make the denominator 0. So this graph will look like this graph. It will just have a hole in it when x is equal to positive 2, because I eliminated that. Let me actually show you this, if I can. Let's graph this feller here. X minus 2 divided by x squared minus 4. And this is the graph, although don't believe it, friends. You went and believed it, didn't you? You believed it. It's lying to you, though, or the computer software is incapable of representing it accurately. But as far as it being at 2, what I'd like to point out is technically at x equals 2, there should be a little hole right in this graph, right there. But other than that, the rest of the graph is accurately represented. And then notice that the end behavior, you can in fact see that this is getting closer to 0 for a y value, and this is getting closer to 0 for a y value as x goes to infinity or x goes to negative infinity. So, I mean, you could really, to put this in layman's words, the y is getting closer to 0 as the graph goes to the left, right? And the y is getting closer to 0 as the graph goes to the right, is essentially what that's saying there, right? And you can see that based on the horizontal asymptote. That was a terrible asymptote there, but that's fine.
Isn't there another hole for x equal negative 2?
Actually, no, because that one is still included in this graph itself at x equals negative 2. And in that case, it's actually an existing vertical asymptote.
Oh, okay.
Yeah.
Okay.
Yep. I guess you could say that this horizontal is a bad asymptote, but that might seem inappropriate for someone to say. Hopefully no one ever edits just that one clip out of my lesson and then uses that against me. That would be sad. So let's talk about monotonicity. I know. Yes. I probably won't. Or maybe I will. Maybe I'll just sneak into this building once in a while. Teach math to an empty room. Yeah. Oh, I forgot to copy the part that said monotonicity, because that was actually important, the name of it. So the monotonicity of a function is essentially, I'm describing where is it increasing and where is it decreasing. That's what I'm trying to describe. Monotonicity. So function f is increasing on interval I if and only if for every a and b contained in I, f of a is less than f of b, whenever a is less than b. So that's essentially describing the points to the left are less than the points to the right. Right, like if you imagine a little graph here, it's increasing, even if it's like got like little swervy curvies, like so. If say here's A, here's B, the heights of those points would be f of A and f of B, and you could see that the y value here is in fact lower than the y value there. That's all it's saying. That, right? It's increasing because it got bigger, right? Super analytical.
Oh, I learned that in first actually.
You learn monotonicity?
Yeah.
What's the word?
Yeah, what's the French word for it?
I don't remember.
Alas.
Great.
What if you found out you went back to France and then didn't understand anything anyone was saying because you forgot the whole language?
I would speak English?
Yeah, like you realize like, oh no, I don't understand what anyone's saying anymore.
That would suck.
My brain has unlearned French in the last year, and now I only speak English.
Yeah. That would be sad. Maybe I would have to come back.
Yeah, yeah. Well, what percentage of the population speaks English?
Almost everyone. I mean, you need to take it in school.
Right. Do people speak English regularly, or just
No,
like
never.
for us jerk visitors?
Just in class. Yeah, and jokes and visitors.
Yeah, just like I demand you speak my language when I visit your country. Like,
Yeah.
yeah. Mm-hmm. Mm. What a shame. What a shame. So I think you guys agree that this graph would be increasing because f of b is, or actually I'll say it in the order it's in. F of a is less than f of b, or I could have said that f of b is less than f of a.
What?
The y value here was less than the y value there. So therefore, in between here, it was increasing.
Yeah, but then you said I could have said it the other way.
As long as I said f of b was greater than f of a. I don't know. Go back and replay the video.
Yeah, you said B was less than
I'm sure I did.
A. Okay.
I'm completely certain of it. So, and then I also describe decreasing. So we've got increasing, decreasing, and then constant. And of course, in a constant function, the y values are the same all the time. Todo de los tiempos. So do we, still writing? I won't redraw a picture for decreasing or for constant. I think you guys get the idea. Monotonic. I think monotonic as a word became popular in the 1950s because there was a soda brand, like some sort of pop beverage that could have been just called monotonic. I think it would have been a pretty good name. Ooh. Actually, guys, I think I'm just coming up with an idea for an energy drink called monotonic, and I would say your energy will be increasing or constant. Would it? Yeah, that would fail.
Your energy will be exactly the same.
Fire product anyway.
Yeah.
We'll feel exactly the same.
Hmm.
That's what a mono is on.
Yeah, mono. Well, the mono in this case is actually regarding the fact that it's consistently increasing or decreasing. So it is doing the same thing. It's just increasing or decreasing. Question. So let's talk about a couple little examples of this. Exemple. Perhaps I could phrase it this way. Determine which intervals for which the function is, on which the function, how about? Yeah, these sound like words. The function is increasing or decreasing. And let's say I had the function, I think we're going to analyze two of them. Let's analyze good old f of x, our friend of x. 3 minus, actually I'll write it this way, negative parentheses x minus 5 all squared. Yikes. Oh, I'm getting some lag here. Here we go. Plus 3. And tell you what, you probably would know that this is a parabola. You probably know that its vertex occurs at positive 5, positive 3, and then it's opening down and is a regular shape besides that. Let's just giraffe this one for fun. It'll come back, don't worry. Negative parentheses x, what is it, minus 5 squared plus 3. Sounds like, bam, there we go. So there's my little giraffe.
So we still don't have any graphics.
Well, this is a parabola. You've seen these before. You could graph with technology, though, tonight if you wanted. Oh, my apologies. So, where is this graph increasing? Looks like it's increasing here. It's going up, 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 up. And then it's decreasing after that, right? Down, 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 down. Is how I taught Everett to say down when we're going downhill in the stroller. Down, down, down. Like the key is, the pitch is changing. Versus up, up, up. Like, it's pretty good. Pretty good. So, So over what interval is it increasing? Well, it looks like 5 is the changing point right there. So it is increasing pretty much for x is less than 5, right? And it is decreasing, decreasing for x is greater than 5. Right? So that's not too shabby.
You don't have to find a constant?
No. We're usually just interested in the increasing or decreasing. And this concept is actually going to tie into calculus maybe by the end of the week or maybe next week, this whole idea. And we'll actually have a really effective, efficient way to determine where a function is increasing, decreasing, or where it's constant, as you so amply put it. So I think we'll call it a video. What do you guys think? You want to see another picture of
As you amply put it.
amp?
Aptly.
Aptly? Doesn't matter. I think he put it in an amp. Yeah, that's fine. Yeah, I said it the way I say things, which is with syllables. And that's sufficient. Thanks for watching, Internet friends. Bye-bye.